So in the first part of the presentation, we looked at different types of horizontal heat exchangers. In the second part, we'll take a closer look at the soil thermal parameters that are important for the design of those systems and the specific problems that we have when designing these type of heat exchangers. Especially soil thermal conductivity and soil heat capacity that depend to quite a high extent on the soil moisture content, which may vary over time, and of course the seasonal vertical temperature gradient, which is important near the Earth's surface. So let's start with the soil thermal conductivity and heat capacity. The first question is, where can we find reference values? And the answer is they are tabled, for instance, in the European norm 17522. We see here a little table, and I have highlighted for clay, sand, and gravel the typical values for dry and water-saturated situations. And we find that for clay, for instance, the variation is 0.5 for the thermal conductivity in watts per meter Kelvin for a dry environment and 1.8 for a saturated environment. For sand, typical values range from 0.4 for dry to 2.5 for saturated environments, and in practice they may even be higher, up to 3.5 or so. For gravel, again, a quite big difference in soil thermal conductivity, 0.4 for dry situation, and again 1.8 or even higher for saturated situations. So this is for the thermal conductivity. We can do the same for the heat capacity, but there is another way in which we can assess heat capacity, and that is by calculation based on a formula where we have a value for the porosity and a value for the water content and a value for the mineral fraction. The formula is given below. So if we know the amount, the ratio of organic material multiplied by 2.7 plus the ratio of mineral material multiplied by 1.9 and the fraction of water multiplied by 4.2, we get an overall heat capacity. Now there are two things that we can vary. That is the porosity value itself. For instance, in the table you can see 25 or 30%, pretty representative for sandy deposits that we find in the Netherlands. And the water content then can be 0, so dry, completely dry, can be 50% or 100%. And we can see that the heat capacity range will be somewhere between 1.4 and 2.6 megajoules per cubic meter Kelvin, so quite a high range of values. Then the temperature. Again, a nice formula with which we can calculate the seasonal temperature variation as a function of depth. We need to input the average surface temperature and the amplitude of the surface temperature over the year, and then we can calculate with this formula the temperature for each day of the year at different depths. And we can see that at shallow depth 0.05 meters, we have a high amplitude of surface temperature, almost ambient temperature values that we find at 1 meter and 2 meter. We still have significant changes in temperature, but when we go deeper than about 5 meters, again, this is the situation for the Netherlands, we have a very small variation of seasonal temperature in the ground. So what is the effect of these values on the actual design? We've taken here as an example a design calculation for a ring collector type, slinky type ground heat exchanger with a heating load and a cooling load that is 1.3 times the cooling load. So we extract more heat from the ground than we put back into the ground. The reference value for soil heat capacity, 2 megajoules per cubic meter Kelvin. And then we did a calculation for different soil thermal conductivity, 0.5, so dry soil, 1.5 moist, and 2 wet soil conditions. What we can see in the graph actually when we focus on the low and the average, the typical soil thermal conductivity, we can see that with a low soil thermal conductivity in winter, the temperatures are significantly lower, and in summer the temperatures are significantly higher. We can also see over, let's say, the first 5 years or so that there is no, let's say, build-up of heat or buildup of cool in the ground that we would expect with a vertical borehole heat exchanger, where more heat is extracted than injected, as is the case in this example. If we take a look at the difference between the average, let's say, soil thermal conductivity of 1.5 and a high soil thermal conductivity of 2, we can see that the effects of the soil thermal conductivity are much smaller. So basically, the conclusion is that a low soil thermal conductivity has a high effect, but a higher soil thermal conductivity has a smaller effect on the design temperatures. Doing the same for the heat capacity, the effect of soil heat capacity, we see that if we vary this about the same magnitude of change, 1.25, 1.75, or 1.25 megajoules per cubic meter Kelvin, with a soil thermal conductivity of 1.5 watts per meter Kelvin in all cases, we can see that we have some variation of temperature in summer and winter, but not as big as we had for the soil thermal conductivity. So, in summary, we can say that the near-surface seasonal temperature variation and gradient are important for the design. This means we need to have a good knowledge of local temperatures. The shallow soil thermal parameters depend on soil type and moisture content. They can be quite variable, and this we need to take into account in the design. One thing we didn't discuss is freezing. Freezing may enhance heat extraction, but introduces soil mechanical effects and maybe should be avoided. And in certain countries, it is also not allowed. Like in the Netherlands, it's not allowed to freeze the soil. Moreover, it's quite difficult to calculate and design for. Thank you very much.